So, students, we discussed electronic configuration of actinides, and if you remember, we placed 86 electrons of radon in respective subshells. Now, uh, the actinide, which had electronic configuration beyond this radon, was 7s2, 6d1, and 5f2. And this is actually a violation that electron do not occupy 5f0 while it occupies 6d1. Then in case of thorium, again the violation is there, and two electrons in 6d have been accommodated, and this has been predicted on the basis of or proved on the basis of chemical reactivity of this species. In protactinium, then one electron has been occupied by 6d1 and 2 by 5f2. Then the electronic configuration proceeds in a normal way with the same violation of electronic configuration rules. Then for plutonium, the electronic configuration obeys electronic configuration rules. There is no violation. For next, americium is also no violation, and for curium again the violation is there, and this violation can be explained because of the half-filled 5f or subshell, where one electron beyond this half-filled, it is accommodated by 6d1. Then the electronic configuration continues until the end of the series. The electronic configuration obeys the electronic configuration rules. Now let's summarize the series, that there are violations, and violations are, if you compare it with lanthanides, so they are more than lanthanides, because in lanthanides there were hardly two or three, but for sure there were two violations in electronic configuration, and in case of actinides we have some more violations, so total violations are now six. If you remember general electronic configuration of lanthanides, where d orbital was capable to accommodate maximum one electron, while in this case d electron has accommodated maximum two electrons, and the only case is thorium, where two electrons have been accommodated by 6d2. Rest of the elements, they possess one electron in their d subshell. So this is all about electronic configuration of actinides. And next we move toward oxidation state. So just like lanthanides, actinides also possess variable oxidation states, and there are various possibilities. But what we have to discuss, we have to take to consider only M3 and M4 the oxidation state. So actinides, they most of them they possess +3 oxidation state up to the end of the series, and also +4 oxidation state has been observed for almost all actinides except for actinium, which is actually not actinide because there are only 3 electrons in valence subshells, or we can say that penultimate and anti-penultimate subshells. So since there are no electrons beyond this m+3, therefore it does not adopt m+4 or even above +4. Now in this case, if you look at the electronic configuration in oxidation state of these elements, so starting from F0, so F1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Now here exactly the electronic configuration rules have been obeyed by the series. So oxidation state +3 is easier as compared to normal electronic configuration of actinides because there is no violation in the series in M+3 oxidation state. In case of M+4 oxidation state, where M represents generally actinides. So again starting from 0, 1, 2, 3, 4, 5, 6, 7, 8 and up to 13. And again, there are no exploitation or violation of rules in the series throughout, starting from thorium to lawrencium. Now, if you look at oxidation state of actinides, so in many cases you can find actinides up to +7 oxidation state, and up +7 oxidation state, the most stable state is neptunium, and this can be justified because the neptunium in +4 oxidation state, it possesses 3 electrons and 5 F, and whenever it lost 3 electrons, so the total number of the oxidation state of this neptunium will become +7, and in that case it will have no electrons in valence shell, therefore the system will be more stable, and rest of the systems, depending upon the situation, we can explain why higher oxidation state has been adopted. But as I told you, they can move up to +7 oxidation state. So this is the only difference between lanthanides and actinides, because for lanthanides the maximum oxidation state was 4, and in that case there were only 4 elements. For 2 we were able to explain that why they exist in +4 oxidation state, while for 2 normal electronic configuration rules failed, that why they exist in +4 oxidation state. And then after electronic configuration failed, we were able to consider other factors that can be the geometry around the metal ion, the environment, the medium where they were present. So normal rules were not able to explain the +4 oxidation state. But in short, we can say that +4 was maximum oxidation state of lanthanide, while for actinides the oxidation state starts from +3 and it reaches to +7. So maximum oxidation state has been achieved by these elements. Now we will also discuss further chemistry of these elements, and in start we also discussed that these elements are very less in the series are naturally occurring, and up to neptunium the first 5 elements are naturally occurring: actinium, thorium, protactinium, uranium, and neptunium. While plutonium and onward, they are not naturally occurring, they are radioactive, and their half-life is very short as compared to the life of the Earth. Therefore, in Earth crust, they cannot exist freely, but they can be synthesized in the lab, and depending upon their lifetime. So in that, during the half-life of these elements, we can discuss or we can determine certain properties of these elements, but most of the properties are not known because of the reason that they are radioactive, and because of their radioactive toxicity they cannot be handled in ordinary labs. So sophisticated setup is needed, and that setup is not available in every lab. Therefore only specified or specialized people are able to discuss or to study properties of these elements. Next in, let's summarize the oxidation state of these elements. So oxidation state in common, just like lanthanides, is +3. So this is one common feature of both the series lanthanides and actinides. In both the cases, common oxidation state is +3. +4 oxidation state is also observed in most of the cases for actinides. And this +4 was not observed for lanthanides, because for lanthanides, as I told you, there were only 4 elements, 4 metals which were in which exist in +4 oxidation state, while actinides almost all possess +4 oxidation state. This is probably because that 4f orbital subshell, they are deeply, these orbitals are deeply buried and not readily available for bonding. The ionization beyond +3 is energetically not possible in case of 4f, while in 5f the energetic the energy consideration of the system, they allow oxidation state beyond +3. So therefore actinides can be can be found in plus 4 or even 4f orbitals are deeply buried in the structure of lanthanide series, and therefore electrons beyond this m plus 3 were not easy to be kicked out from the 4f orbital. Therefore, the oxidation state beyond plus 3 was energetically not possible. If we compare the energetic consideration of actinides, so last electron has been accommodated by 5f, and in this case 5f is logically it is far away from the nucleus, and electrons can easily be kicked out from 5f orbital in case of actinides. Therefore, energetic considerations allow the kicking out of other electrons beyond this plus 3 from actinide series. So higher oxidation state for actinides is feasible as compared to lanthanides because of these energy considerations. The 5f orbital it is further extended and is involved in covalent as well as ionic bonded, making the chemistry of actinides more complicated as compared to lanthanides. And this we will discuss in case of coordination sphere of lanthanides and actinides. So lanthanides will have very limited coordination sphere, and in case of actinides the coordination sphere will be more expanded. So these elements will be capable to make more bonds as compared to lanthanides elements or lanthanide metals. The oxidation state further extends to reaches plus 7, and as we discussed for neptunium, this was the most stable because in neptunium all valence electrons have been lost in order to attain this plus 7 oxidation state. But the stable one for this species is also plus 7, which has been experimentally observed. For thorium and californium, they possess plus 4 oxidation state. Berkelium is more stable than curium, and americium is it is F7 system. So this can be explained now that why berkelium plus 4 is stable than rest of the partners of the series. Nobelium is markedly stable in plus 2 oxidation state due to F14 system. And again, this is also an anomaly because plus 3 is common oxidation state as we discussed at the beginning of this slide, and this is plus 2. So plus 2 can be explained only on the basis of this completely filled F subshell. Due to high charge up to plus 7, the ion is no longer a simple ion as we are discussing in general chemistry that whenever electron is lost, so how bare ion looks like or how it will exist in the solution or any other suitable medium. So they are highly active because plus 7 oxidation state it impart too much nuclear density to the atom, and because of this this charge density, sorry, the charge density, it is highly reactive, and on the basis of this reactivity it cannot be as free ion or in solution or any other medium, and it exists as oxygenated ion, and this oxygenated ion is normally a cation. So oxygenated cation ions, they are not normal for other elements, but this is the only characteristic feature of actinides, and such oxycations they are stable even in acids and in water. So it means that these cations can be isolated, can be characterized, and can be studied in detail because they are highly stable even in water and in acidic solution. Thank you very much.